recap from last time, since we didn't finish all the slides, we'll just take the first hour to go through the last slides, and then we'll start with the full tutorial. So like you will be using your computer a little bit. So let's briefly recap what we said last time. We talked about formalization as a whole, which means taking some mathematical statement definitions or proof and translating them into a formal system so that the computer can check its correctness. We talked about why this is useful and interesting, and we've shown a few examples of Lean code, and now we're going to show. We've already seen one example of formalization project last time. Now we see a few others. So Lean has been around for some years now. Let's say it's been more famous in the last 4 or 5 years. So the projects I will be showing you are all from the last 4 or 5 years. The first one, we already talked about it, is the liquid tensor experiment. Now, these are the two of the people involved. One is Peter Schulze, who did not write the code, but he wrote the mathematics behind it, which is condensed mathematics. And the other one is Jan Pommelin, who was the leader of the formalization effort. And as I said, this was probably the first real Lean project where it both involved complicated mathematical objects and complicated proofs. So we wanted to prove, they wanted to prove hard things about hard objects, and it made the news for some time. It was one of the key points for Lean to be known more to the general public. Other notable projects are, for example, the sphere version project. It was done by Floris van Doorn, Patrick Massot, and Oliver Nash. And let's see a little bit the like how the project is organized, because this looks a bit more the more modern projects. I have to this out. Okay. So usually now when you start a big formalization project and you want people involved from all around the world, you usually make a web page so you can show your project to others, you can make others interested. And this is the Sphere Version project web page. From this page, you have access to all the important bits of information about the project. Here there is a brief description of it. You can go to the blueprint. We already saw the blueprint of the liquid tensor experiment last time. And this is essentially all the mathematics that need to be formalized. So it's basically rewrite of the paper, but in a more formalization-friendly way. So the theorems are split into smaller lemmas, and the proofs are given in much bigger details. We can browse it, and just like the other time, we can go to the dependency graph to see how the project is going. In this case, this project was finished a few years ago. And we can see that because all the bubbles are green. Other important projects were the Flypitch project, where they proved the independence of the continuum hypothesis in Lean by Floris van Doorn and Jesse Michael Fan. Now the polynomial from Arusha is a bit nearer to us because it was started just last year, and it was also completed last year. And this was done by Terence Tao. It was the first time where like such an important and well-known mathematician started to write Lean code himself. In fact, Terence Tao did not only prove the mathematical content of this project, but he also led the formalization effort. He started formalizing Lean himself. And he's been involved in Lean a lot in the last 1.5 years. In fact, just a few days ago, he started publishing YouTube videos where he formalizes stuff, for example, with the help of GitHub Copilot and other AI-assisted tools. The biggest project that's currently ongoing instead is the Fermat-Last theorem project. This project, as the name suggests, is an effort to formalize the famous proof of Fermat's theorem. It's led by Kevin Buzzard, who's the leader of the formalization effort, but also Richard Taylor is involved. Richard Taylor was, together with Wiles, he finished basically the proof of Fermat's theorem, and he helped also write the blueprint for this formalization project. They actually simplified a bit the proof before even starting the formalization project. So the proof that will be formalized is basically a new one, taking, of course, some material from the old proof. And this project is huge. Okay, the other projects we saw were all completed in less than a year, maybe. But Fermat's theorem is completely on another scale. In fact, Kevin Buzzard has a 5-year grant which started last year solely to formalize the project, this theorem. But he doesn't want to formalize the whole proof. In fact, he says it would take too long, even if it has like 5 years. He only wants to formalize the last part. So everything that's he will assume true everything that was before the 1980s, that was done mathematically before the 1980s, and then formalize the last few years. Another interesting project is Carson theorem, which is done in Bonn. This is still an ongoing project. So if you know some harmonic analysis and you want to try to contribute to it, it's a great place to start. They are welcoming contributions. And already people who also do not know about harmonic analysis have already contributed to the project successfully. This project, as I said, is still ongoing. So we can go again on the page and we will see the HTML blueprint. And the dependency graph is still not completed. It's on its way to completion. You see the bubbles, which are not green, are all blue, which means they can be formalized in the near future. They do not need any more dependencies, but still they're going to complete it in the next few months, probably.
The project about the Fermat.
Sure.
That is assuming that the mathematics for a certain year is already through. So like there is a way lean to like assume this goes through and this really easy to do, or is something really difficult to like give something like say this is true and
So no, there's an easy way to do this.
okay.
You can just now we'll see this a little better when we start the tutorial. But you can just put a keyword which is sorry and instead of the proof. And sorry basically can prove anything. So you can say, okay, here's my statement. You write by sorry, and Lean will accept it as true. But sorry relies on an axiom, which is called the sorry axiom, with which you can basically prove anything. And so Lean will let you know when you're using an additional axiom. It will let you know right away on the proof that contains the sorry, so you will get some warning there. You will not get warnings in proofs that depend on this, but you can trigger the warning yourself. So Lean will not actively tell you, wait, here, this result depends on a sorry, but you can do print axioms and then the name of the theorem, and it will print all the axioms that are that this theorem depends upon. And if sorry axiom is there, you know that you basically have some hole in your proof. Now this is a bit you have to be very, very careful when you assume results to be true without proof, because it's very, very frequent that edge cases are forgotten. So you have to be like, just to check your statement multiple times, because it's easy to miss some like edge cases usually, which maybe make the result trivially true or trivially false.
Because I was thinking like, you don't have, if you want to prove a result, you don't have to prove or formalize all the mathematics beyond, but using this story is okay.
Yes, that's a way to, instead of having to like to build all your structure, you can put something in the air which more or less holds, but you have to be very careful that the thing you're assuming is actually true, because of course this takes away all the the complete trust that we put into the system. If we assume things arbitrarily, we cannot like trust the truthfulness of the result of the end result anymore. No. Please make as many questions as you as come to mind. As you can see now, the blueprint for Fermat's last theorem is huge. In fact, it doesn't have a single dependency graph. It has a graph for each chapter, because it would be okay. This is not completely done yet. Okay, yes, some chapters already have a graph because also the blueprint is being written together with the project. It's not it's too big to be completely done before starting the formalization. Okay, so let's look at another project that highlights another critical aspect of Lean, which is the equational theories project, which is another project from Terence Tao. I told you he's very interested this time. And the equational theories project is actually not a project to formalize all the mathematics, but this is a project to formalize new mathematics and to discover new mathematics at the same time as the formalization is done. Now the idea is the setting is super simple. We are dealing with magmas, which are just sets with a binary operation which goes into the set itself without any other property. And the idea of the project is to find which equational laws imply each other, where an equational law is something like the commutativity law. So x and y, x times y is equal to y times x. But it can be anything. For example, if you look at this image, okay, you can see, for example, we have the trivial law at the top, which says x is equal to x. That's true for any magma. At the bottom, we have laws that are equivalent to x equal y. All of them are quantified with for all x, for all y, for all z, etc. So if for any x and y, x is equal to y, we have just a single element in the magma. So that's also a trivial law. And this is only satisfied by the trivial magma. And all the other in the middle are laws that are satisfied by some magmas, but not by all. And this Hasse diagram describes how they imply each other. So if a magma satisfies like law with number 4, it will also satisfy the law with number 4522, for example. And why is this project like very different from the others?
Usually a project is a theorem that they want to prove. So what is the formula, the theorem, the sentence that they want to fulfill?
That's a caveat. There's 22 million of those that we want to prove in this specific project. In fact, the Terence Tao, of course, you have an infinite number of possible laws because you can just continue adding new variables and continue making the law longer. So there's an infinite number of them. And it was decided to stop at all laws which contain at most 4 operators. So 4 occurrences of the operator that in this case is indicated by the diamond sign. There's a bit more than 4,000 of these laws. For each pair of these 4,000 laws, the question is, does law A imply law B? And that the theorem, the theorem or its negation is what is to be proven in this project. Of course, proving 22 million theorems is too much for anyone, for any group of mathematicians. It's really a number that's extremely large. So how did we? How was the work like? How did they manage to complete it? Because it's complete now. What was done is to use a combination of human provers and automated theorem provers and machine learning to automatically prove most of these implications either true or false. And this was allowed by the fact that basically, if you give, for example, a SAT solver is a very general solver for logical formula, and they are very powerful pieces of code. They can solve what's called the satisfiability problem very fast. And a lot of problems can be reduced to some form of satisfiability problem, and so can some of these implications. So what was done is you take programmatically, so algorithmically, you produce the laws, you convert them into some code that the SAT solver can ingest, and you make the SAT solver prove or disprove the law. After you do that, the SAT solver will give you some kind of certificate that that the implication is actually true. And this can be converted into Lean code with some effort. And Lean will actually certify that this implication holds true or false for us. But that's only possible because of Lean, because otherwise we would not trust that the machine actually didn't make any error, because SAT solvers are internally like complicated pieces of code. They can be faulty, they can have bugs. And so this is really an example of how Lean allows you to collaborate with the machine and also to collaborate with other people, because a lot of people contributed to the project, both with code, so to produce the proofs, to solve the implications, and to manage all this data, because, as I said, 22 million implications it's a big number, even just to browse or to look at what's been done or not. Of course, not all of them were easy enough for SAT solvers to solve, because SAT solvers basically explore algorithmically the space of proofs in some sense. But the space of proofs is huge. It blows up very fast, so it's hard to solve this algorithmically. And some proofs were done actually by humans, and were first they were proven by humans on paper, and then they were formalized by humans. Let's see if we can look at some of the. Okay, so this project is as I said, it's huge, and it has a lot of related code. So there's blog posts about it. There's a lot of information about the things that were used. These are all the SAT solver, the automated theorem provers that were used, because not all of them are SAT solvers. And there's a lot of code to be seen. So yes, here is the blueprint. For example, the dependency graph, it's huge. Also, this of course doesn't contain all the implications. This was done manually, and it only contains like hard things that are needed to prove the hard implications. Okay. And now just two last examples of projects which are not. The equational theories project is basically completed. All implications have been proven, even though there's a variant which only consider finite magmas, where one implication still remains to be completed. It will probably just remain a conjecture. Now, these other projects instead are not completed, are in the earlier stages. So there is this sphere packing in dimension 8 project, which was started last year, but it's still closed. So not everyone for the moment is allowed to contribute, at least from what I know. And another project that's being started just this month is the 3 geodesics project, where they want to prove this theorem in differential geometry, the theorem of the 3 geodesics, if you have heard of it. And it's actually being started partly in Italy, because a group in the University of Trento will probably make some contributions to the project. It's still not clear who will be the leader of the project. But if you're interested in things around if you could be interested in differential geometry or things adjacent to this, you can try and contribute to this project. They will certainly welcome external contributions. Okay, now let's go to some tools which can be useful during your formalization journey and while learning formalization. The first things I want to point at are the community resources. As I told you last time, Lean has a very active and welcoming community. The first place you want to go if you want to know a bit more about Lean is the Lean community website. Basically, everything that there is to know is there. You can have a look at it, and there's a lot of things to going on here. There's papers about Lean, for example, events on Lean if you want to go and learn a bit more at an actual event. There's how to get started with Lean, where they walk you through the installation. So if you want to install Lean locally, which I suggest you do if you want to continue working with Lean after these lectures. You know, it's not necessarily for the lectures, but it's definitely the way to go if you want to work for more than a few hours with Lean. So I would suggest you get started here. And there's a pointer to the online version of Lean. That's the one that we will be using in the next hours. You don't have to do anything. You just click here and you can start to code. And if you don't make mistakes, okay, it's a mistake. See if it does. Yes, it does. Okay, so other things that can be useful are the Zulip chat. So Zulip is basically a forum, an online forum where all the community goes to ask questions, coordinate projects, and you can go there either to seek for help or to start a new project, to propose a new project and see if other people are interested, or to be informed about the latest news about Lean events, the new releases, and all of that. And GitHub instead is the platform where the code is usually hosted. So if you've never used GitHub, this is an online platform where developers can put code. You see, now, this is my dashboard. I can see some projects. There are also some Lean projects. For example, MATLAB4, the mathematical library, is hosted on GitHub. You can go here to look at the code. Here are all the folders inside this repo. For example, here we have method folder, and we have all the mathematical branches which are inside of MATLAB. We can go to analysis. We can go to calculus, and then we can go into some file, and we can see all the Lean code. Of course, this is useful if you just want to give a very quick look. But if you want to interact with the code, GitHub will not let you use the info view, for example, so the interactive mode. So you will have to download the repo into your own system, or to copy and paste. If you just want to have a very quick look at it, you can copy and paste the file into Lean4Web and hope everything compiles, because sometimes maybe they import some local files, so it will not compile on online version, of course. Okay, now let's go to the project management tools. I already spoke about Lean Blueprint, actually. This is a separate piece of code from Lean, and it's used to to make Lean interact with the latest document. And it's the piece of code that produced all those things we saw on the project. Let's see where it is. For all of this is produced starting from this LaTeX code in Lean Blueprint. The graphs are produced. Okay, here's just one note, but they are produced automatically, so you don't have to separately write the blueprint and the graph. They will be done at the same time, and you can also compile this into a PDF, a separate PDF with the same content without writing anything else. If maybe you want to, have it on your desk. If you really want to start a project, the first thing I suggest you do is not to download Lean Blueprint, but is to go to the Lean project template. This is another GitHub page, and it's not a separate piece of code. This is just a template for your Lean repository. It's very well documented. Everything that you need to know to use it is basically written here. There's also some YouTube tutorial here if you want to be walked through the use of it, and you can use it to basically to start your project without having to fight with the blueprint installation too much. When you actually want to write some Lean code, there is a few tools that are really, really important to have. So the first one, so as I said, if you're just doing your first lines of code, you can start from the browser, but you will soon notice that you would like to have, for example, a file management system, and you probably want to write code maybe when you're offline. So you would like things to be locally on your computer. To do that, you need some interface to interact with your code. And the one that I suggest is VS Code. That's the most used one. It's used a lot to program in many languages, Python, C++, basically any language, because it's extensible. So you can just download the extension for your preferred language. And there's also the extension for Lean. Let's see if I can, for example, open like the equational theories project in VS Code. That's what it looks like. And here we just went into some random file inside the equational theories project that we saw before. And you can browse your files. Now there's a ton of them, of course, because the project is huge. But your project at the start will have just a few files. Here we have the info view. You have this orange line that tells you that Lean is currently running this file, because all files in Lean are run at the same time as they are written. So if you change a line here, for example, let's comment out this line, Lean automatically tells us, oh, you made something wrong. And it gives us a mistake because we deleted the line, basically. So we don't need to push any buttons for Lean to check that our proofs are correct. So VS Code is basically the top choice of most of the community. If you really like Emacs or Vim, there's also extensions for Lean in Emacs and Vim. But I mean, I don't suggest you use them unless you are already used to Emacs and Vim. Another tool that's very important is Git. Git, as you may have noticed, is the first part of GitHub. They are not like directly correlated, but they do similar things and they interact with each other. Git is a tool that's used by computer scientists to do version control. So you're developing a project, you're making changes, but you still want to keep a history of how your project proceeded, because maybe you make a change and a month later you say, oh, wait, I shouldn't have made that change. I want the previous version of my code, and a version control system lets you do this very easily. And it's needed to run basically any Lean project. It's a requirement, for example, for Lean Blueprint. It's also very useful for collaboration, because maybe we're running the same, we're doing the same project, we're making changes to different files, or maybe the same file at the same time. Of course, I don't want to see the change of the other person in live, because it will mess up everything. But I want to be able to keep both changes and maybe make the right adjustments to them to put them together. And all of this is made not so hard by a version control system. Another tool, now this is not really necessary to use. You can choose not to use it, but it's really a good power up especially if you're just starting to use Lean. Now GitHub Copilot is an AI-powered assistant, and it runs like live on your VS Code editor, for example. Let's see if I can manage to trigger it. Let's say I want to. Yes, okay. I just went 2 lines below, and what Lean Copilot does is this thing here. So it suggests a line of code. Now, of course, here is a completed file, so it just guesses basically randomly. He thinks, okay, maybe you want to make a comment in the code. But if you're inside a proof, it will try to suggest the next step of the proof. Of course, it doesn't always get it right. It makes mistakes, but it also makes very useful suggestions from time to time. It suggests maybe a good syntax, or maybe a good lemma that you could use. And it also has a feature called Copilot Chat, which is up here in my case, where you basically can chat with your code. And it's just like having ChatGPT inside your repository, where ChatGPT can see your code. And it's very useful because it can, for example, explain some code that's not so obvious to you. You can use different AI models, for example, here. Also, if you use an external AI Copilot, is this can be also very useful to start, like ChatGPT. It sometimes messes up the syntax because there was a change from Lean 3 to Lean 4 in the recent past. And Lean 3 has a slightly different syntax than Lean 4, so it sometimes hallucinates and thinks you're writing Lean 3. So it suggests like wrong notations, but they can still be useful because maybe you can just tweak a few things once you get used to it and have actually good and running code. Now, the last thing I want to show you is not necessarily a tool you want to use, especially because it's not public yet, but it's a super, super cool tool that will be probably available in maybe the next months. It's called Lean Informal, and it's not to use wild bright Lean. It's something that you will want to use after, because it lets you convert formal Lean code into informal natural language. Let's just see an example of this. So as I said, the code is not public, but there's 2 examples, 2 demos available. And here we just see the output. Maybe I have to make it a little bigger. Okay. Here we just see the output of this program. So some Lean theorem was given to the software, and it gives us back this, which is an informalization of theorem. And as you can see, is perfectly readable in just plain English. Here's a theorem from the Rudin. It says that let X be a topological space, E a subset of X, then E is open if and only if the complement of E is closed. And here is the proof. And if you see, if you try actually to read the proof, you will be a bit dissatisfied because it just says, okay, we have an if and only if prove. It suffices to prove one direction and then to prove the other direction, and then we're done. And then it says, okay, one can see that the first direction is true, and then one can see that the second is true, which, okay, thank you, not very useful. But we can go actually inside the proof if some passage is not clear to us, and we can expand the passage, and now it will give us additional details. Okay, so it says, now suppose E is open, then blah, blah, blah. It uses a theorem that maybe we don't know about because it's, okay, it's just the name of the theorem inside Lean. What's this? I don't know what it means. Well, that's not a problem because you can just put your mouse over it, and it will give you the statement of the theorem also in natural language. So you don't need to know any Lean to make use of this. It still retains, so of course you can go deeper and deeper until we're satisfied, or until we hit the very bottom of the mathematical proof. It also lets us use the interactive mode in Lean, because as you see, there's these symbols here, and if we click on them, we have basically the translation of what was the info view in Lean, where it tells us what is the current proof state. So what do we have defined until this point? We have a topological space X and a subset of X, and the goal that we have to prove now. And now here it says, suppose E is open. We can go after this line, and it changes. So now we have open, the fact that E is open is inside the hypothesis, and we just have to prove that E, the complementary of E is closed. And this tool, I think it will be huge for mathematical dissemination and for mathematical textbooks, for example, because you can basically choose your own level of deepness, of depth to read the proof. So the same mathematical text can be proposed to an undergraduate student or to a mathematical expert. The mathematical expert will just collapse all the bits of the proof that are trivial to him, but maybe still expand things that are not so immediate for him, while the undergraduate student would probably expand most things. And this is still in, as I said, in development. It's not completely ready, but as you can see, at least on simple examples, it works pretty well. This is all readable. It doesn't make any like strange artifacts. Okay. Now the last thing I want to say, okay, maybe we're going to say this in the next lecture. Actually, we can. I think yes, we can start with the code right now because we will not need to search into the library at least for today. But the last thing I want to show you, okay, yes, one thing that is very, very good for mathematician in Lean is that you can use Unicode notation. So you don't have to write everything in plain text. If you, I don't know, introduce the Lebesgue integral, you don't have to write Lebesgue integral every time you want to use it. You can just give a notation for the Lebesgue integral, like the integral sign, and Lean will know that this means Lebesgue integral and lets you use it to have very nice looking formulas. Now, of course, we don't have an integral key on our keyboard, so we have to write it using some special notation. But that's very easy to pick up because it's very similar to LaTeX notation. Inside your editor, for example, you can just write \a, and it will be automatically converted to an alpha. Actually, you write \a, and then you put like space, or you click tab, because otherwise it will not trigger. So we have all Greek letters. We have some operators. We use this, for example, the /L, which is the left-looking arrow. This will also be useful. The center dot is just a /dot because it's used when you have to branch your proof into multiple sections. You can use the dot to identify.
Lambda is not /L.
Lambda is probably, oh, you have to guess just the first time, or if you want to introduce a new symbol. Because every time you see a symbol in VS Code, if you just put your mouse over it, let's just make an example. So let's see if we have any strange symbol here. Okay, we don't. I will just write one, like in integral. I can just put my mouse over it, and if it will tell us type the symbol using integral. Is it readable? Maybe it's too small. Okay, well, let's get it bigger. Okay, so it says what is the shortcut for this symbol. There's some symbols which have multiple shortcuts, like this can be written with /L or left arrow or minus, like less than minus. But it's very, I mean, if you want to introduce new notation, there's also another place you can go to, which is here. So in VS Code in general, this is the symbol that represents Lean. This is the for all symbol. And if you click on it, it will appear while you're inside a Lean file. And if you have the Lean extension downloaded, the Lean extension is just here. You can go into the extension pages and you have Lean 4. And basically you can access a few features of Lean. One of those is documentation. And you go to show Unicode input abbreviations, and there's a super long list of all the abbreviations and their Unicode symbol. Now, of course, it's not really easy to browse it because there's really a lot of them. There's all the Unicode alphabet, basically. But if you need a very specific symbol once in your life, you may want to try and look for it. But usually you just see a symbol and you hover over it, you know, okay, it's written like this. Now I know how to write it. Okay. Yes, these are all kinds of symbols we can use. Very useful are also the index and pedixes notation, and I mean footnote notation. If you have a lot of variables, maybe you want to number them. And yeah, that's basically all there is to it for the notation. At the end of the presentation, there's just a few useful links you may want to go to if you want to learn Lean. So there's a natural number game. That's a game browser that you can play. That's a simplified version of Lean, but it's nice. It basically lets you construct all the rules of the natural numbers from scratch using Lean. There's also Lean for Web. That's the interface we'll be using. There's a tactic cheat sheet. This is just a cheat sheet with common tactics. You may want to use it or not. Here's where to install Lean, where to go if you want to install Lean. And if you really want to go deeper and spend more time learning Lean, the resource I suggest is Mathematics in Lean. There's a few books about Lean. Mathematics in Lean is probably the one most suited for mathematicians. And it's basically a book, but it's interactive. You can look at it inside VS Code. There's a guide on how to do it at the start of the book, don't worry. and you basically solve exercises while you read the book, so you can learn by doing. Now, let's try to learn by doing ourselves without mathematics and Lean now. And maybe we can do a small break now. And in like 15 minutes, we can come back and start actually using Lean for the first time. Okay, maybe okay, we can start again. And now I will try to show you some actual code and to make you write some code. So please follow me. We're going to go on a web page. Start. Now I will just use the browser and not the links because I think you mostly don't have the links. They are in the Virtuale web page. If someone has access to the Virtuale. But they're very easy to get to just in the browser. So first, we're going to base ourselves on a repository which is called Glimpse of Lean, which has some Lean exercises to start. So what we do is go on the browser and write Glimpse of Lean GitHub. And then we go here, an introduction to theorem proving in Lean for the impatient. So the repo is Glimpse of Lean. So that's just another GitHub repo where there are exercises for events like this. So in cases where we want to try out Lean in just a few hours, and it has its own integration with Lean for Web. So if you had your Lean local installation, you could download the repo from here. You have, of course, you have VS Code, Lean installed, and you can run it locally. But since most of you will not have Lean installed, we can just go into the description of the GitHub page, and down here, where it's written online version, no registration, we can click on read the introduction file. We click there, and we end up here. That's okay. We'll get it bigger. Okay, is it readable? Okay. Now, so here we basically imported one of the files from the GitHub repo directly into the online version of Lean, and we can start to read it and write code interactively inside the file without having to do anything else. Everything is taken care of. We can hear, for example, if you want to change the version of Matlab, but we don't need to now. You can load your own files if you have a file you want to try out, and you can change a few settings here. For example, sometimes it starts dark mode on its own. If you don't like that, if you don't like it, there's probably some setting to revert it. So let's look at how the file is organized. That's the very first introductory file. And the first line that we see is import Glimpse of Lean library basic. Just like in any other programming language, you can import files so that you don't have to write everything in a single monolithic huge file, but you can have your repository modularized and divided into different folders and files. In this case, what we're doing is importing this file, which is called Glimpse of Lean library basic. Now we can do it just because we are in a special Lean Online version. We can see it from here, where it's written project Glimpse of Lean. So it has access to the files of the Glimpse of Lean project. Normally, if you just go here and you write Lean for Web, you can have the same interview without any coding into it. And we can do, for example, as we saw before, import Matlab. Now, as you can see, it suggests us other things to import, because if you do import Matlab, you're going to import everything in Matlab. Most times you don't want to import everything into your file. You just want to import the things you need. Maybe you need algebra basic. Oops. Okay, no, it doesn't suggest it to me anymore. Oh, anyway, I can write algebra, basic, and it will just import the file that we need. Of course, this is a good choice is just to import Mathlib at the start, so you have everything available, and then after you finish writing your Lean code, then you decide what did I actually use in practice, so you can basically prune the tree that you are importing into your system. Okay, so here we're importing some basic library, and then we're doing this namespace introduction. Now, namespaces are a way of organizing your the names of your functions and your definitions. What we're doing here is we're opening a namespace, meaning that everything that's written after this line will automatically have its name to be introduction dot whatever we write. For example, here we define something, and if we over it, it says introduction.seqlimit. So that's the name you wrote, but introduction dot gets added automatically. So if we import our file, if you're in a different file and import this file, we can call this theorem not just by seqlimit, but by introduction.seqlimit. There's also a way of avoiding to having to write introduction each time. Maybe in a new file, I will be using a ton of time the seqlimit, so I can just write open. Now here, since we are already in the namespace, it's open by default. But if we were not in the namespace, we could write open introduction, and it would open the namespace for us, meaning that it will not automatically write introduction before the names of our theorems. But when we use some external theorem, it will try to look not only for the name that we write, but also for introduction dot name that we write. There's, I think, it may either give you some warning telling you there's ambiguity here if you open both, or maybe there's a default one that's used. But yes, that's one of the reasons why not everything is open at all times. For example, you will not be opening NAT, which is the natural numbers environment, because NAT, at least usually you will not be opening NAT, because NAT has a lot of lemma names, which also have another more general version, because NAT is a very, it's a type that's needed very early in the development of Mathlib, actually in the development of Lean itself. So it's more primitive that, for example, commutativity of addition for natural numbers, it must come before basically everything else. So when you go to prove commutativity for more general structures, you also already have nat.adcom. And to distinguish them, we have namespaces. So you usually will not be opening NAT, but you will be opening, for example, measure theory if you're working with measure theory. But yes, you have to be a little bit careful with the name duplication. But usually, if there's a problem, Lean will if there's like multiple statements with the same name and different namespace, Lean will basically let you know, or you will be using the wrong theorem, and you will say, okay, yes, I'm using the wrong theorem because it has a different name. If you hover over something, anyway, it tells you the whole name, just like it tells us the whole name here, even though we are inside introduction. Okay, so that's how you start your file, and okay, here it just tells us some. No, you can have without introduction. We can in the online version. I think you can write at least if you're on macOS Command KC, and you can comment outlines. But that's just shortcut. The easy way to do this is just to go to the start of the line and write dash dash. That's the way comments are made in Lean with double dash. So we can take out namespace introduction, and now this continuous at is just continuous at. It doesn't have the namespace anymore. To distinguish them, sometimes you can write root dot continuous at, and if you write root with these underscores, you can even be inside of a namespace Open again the namespace, and yes, it will not put the namespace in. That's just like an escape sequence to escape out of the namespace, but that you will not probably need it anytime soon. Okay, so here, this is a self-contained tutorial, so it will tell us useful things. Now, we don't need to read everything, but a useful thing is if you want to have bigger characters and your lines are too big, so they go out of your window, you can press Alt Z in Windows or Option Z in macOS, so the lines will do like this. So if the line goes over, it will just come back here without having to go horizontal. And another thing that's useful is how to make comments. As I said, just the single line comment is made with the double dash. While if you have to put multiple lines, you can put /dash at the start and // at the end, just like this. So this is a comment. It starts with /dash. It ends with /. Yes. Now this file starts by giving us a definition. Now this is not how the limits are defined in MATLib, but since it's a very introductory file, we are redefining the limit of a sequence by ourselves here. And we start just like we saw in the other lecture, we start with the keyword def, which tells Lean, okay, we're starting a definition, then the name of our definition, and then the things, the hypothesis, let's say, or the objects that our definition is about, which in this case are U, which is a function from N to R, so it's a real sequence, and L, which is just an element of R. Then after this column equal, we have the actual definition. So what does it mean, seek limit UL? It means this, which is just the usual epsilon delta definition for a limit. So for every epsilon bigger than 0, there exists an n. We're not telling Lean what epsilon and n are, so what types epsilon and n are, because it already manages to do it by itself. Why? Well, because it already knows that this object here is a real number. So if we're saying that something is bigger than a real number, well, it must be another real number, right? So epsilon is already a real number, while n, capital N, it already tells us that it's a natural number because we're saying, oh, it's smaller than small n. Oh, no, sorry. No, there's two passages here, because how does it know that small n is natural? Well, it does know that small n is natural because it's the argument of U. Okay, so U is a function from N to R. So if something is inside of U, then it must be N, a natural number. Now, a thing that's maybe slightly different in notation from usual mathematics is that functions usually do not need parentheses. So we're not writing U parenthesis N, even though that's perfectly legitimate. We can write U parenthesis N, but
The space.
The space is needed because otherwise it doesn't understand what is a single word. So it needs to separate words from each other. There's a few exceptions. For example, if you use like operators, you can avoid putting the space. So the minus operator, it already. What? Yes, I can write this. It doesn't change anything. Also, indentation is sometimes, in some specific cases, it's actually needed. Here, it's not needed. I usually, and also in MATLib, we usually indent the second line, like we write definition, then we indent what actually the definition is like. But as you can see, it's perfectly syntactically legitimate to not to put the tab. Let's keep it though. Okay, so I was saying we don't need the parentheses. And it's usually best not to put them if they're not needed, because they tend to blow up a little bit. If you have nested functions, you will quickly dirty your own workspace with tons and tons of parentheses. So if they're not needed, unless you need them to logically see what's going on, it's usually better not to put them too much. You will still have to put that though in a lot of situations. Great. So now let's go on with the file, and we have another definition. This time it's the definition of continuity. So it's still something which has something to do with epsilons and deltas. The notation is the same as before, but now we have a function from R to R, and the point x0 where the function is where we are saying that the function is continuous at, and the definition is exactly the same as before. We still have universal quantifiers, existential quantifiers, and variables that are introduced but not typed explicitly. Now that we define these two things, let's try to use them to prove something. What? Yes, that's part of the notation for the quantifiers. So if you use the universal quantifier, you'll be saying, okay, for all, you introduce your variable, that comma, and then you put the proposition that is true for all epsilon, for example. Now, one thing you may notice that here we have epsilon bigger than 0. This is actually just syntactic sugar for all epsilon. Now I will keep the old line here, but comment it. We could have written for all epsilon comma, epsilon is bigger than 0. It implies, so we write 2, the existence, so it implies all of this proposition. But Lean allows us to use this little like shortened notation that we just need to write for all epsilon bigger than 0. So the hypothesis that epsilon is bigger than 0 is automatically put inside the first part of the for all. And this can be done also with the exist. You see there's delta bigger than 0. Okay, so here we basically write a theorem about the definition that we made. Let's try to understand what it says. It's an example, so as I said last time, we don't need to give a name to it. Instead, if we wrote like lemma or theorem, Lean will complain because we didn't give a name, so we could write it my lemma, but with example, it's not needed. We don't need to reuse this result. Okay, let's read what's in there. We're introducing two functions. One is a function from R to R, and the other is from N to R, so a sequence. We're introducing a real element, and we're saying that the sequence converges to x0, and also that the function is continuous at x0. So what we want to say is, okay, stick limit f composed with u at f x0. So the function f composed with u, which is a function from N to R, so a sequence, has its limit at f of x0. That's a very simple theorem. But let's see how it looks like once we go into the proof. We start by. I said last time that we have two modes in Lean. We have tactic mode and let's say term mode. And we want to use tactic mode, but they're both useful because sometimes you really just want to prove a very easy theorem, so you just need the actual application of another lemma to a specific case, maybe, so you don't need the by. But let's try to stick with the by for now. It's usually easier to work in the tactic mode. And while we go inside the proof, all of these are comments, so they do not change the info view. You see everything here remains the same, even though we change the position of our cursor. And it tells us what's the situation in the proof, with all the things that we have defined and what we need to prove. Now, how do we prove this theorem? Well, first, we may want to know what sick limit means. Okay, it's true that we just defined it, but maybe it was defined by someone else. Maybe it's something imported by the file from somewhere else. So what we do first is to unfold the definition. And to unfold the definition, everything we need to do is write unfold and then the name of the definition. So we do unfold sec limit, and you see it transforms our goal from this to this. It's usually to browse your proof is usually useful to go back and forth a few times between two lines to see what's changed. In this case, basically everything changed, but sometimes maybe just a single variable has changed. So I suggest you put your cursor at the start of the line so you can do this easily. And now we need to prove all of this. Now that's a fairly complicated proof, so we will not go through all of it, but we'll just look at how the goal changes during the proof. So don't try to understand each line for now. We'll introduce these tactics later on. But now the first thing we do now is introduce a few things. You see, we define delta, delta pos, and HF. And after we write obtain, they get into the context. This is basically from this hypothesis HF, which tells us, okay, F is continuous at x0. So we give it a specific epsilon and the fact that epsilon is positive, and it will unfold the definition automatically for us. So we don't always need to unfold definitions, but we can do it if it helps us our understanding. So now we have our deltas. We can also use the hypothesis that the sequence of the limit of the sequence is x0, and unfold it again with some specific constant, in this case delta and delta pos. So now we introduce these two new variables, n and n is a variable, hu is a new hypothesis, and then we want to show that there exists something such that blah blah blah. And we say, okay, it exists because it's our n. It's the n that we have just defined. So we say use n. We introduce variables, which are in this case n, small n, and the hypothesis that it's bigger than big N. We apply a lemma, an hypothesis that we have the continuity. And we're basically done with the last hypothesis that we had unfolded before, this HU. You see, once we're at this point of the proof, we basically need to prove that this stuff is smaller than delta. And if you look through the hypothesis, we have that for all n bigger than capital N, this stuff is smaller than delta. So we actually have the hypothesis that we need. We just need to apply it using the tactic apply, in fact, with the right n and the right proof that n is bigger than capital N. And after we do this last step, what we see is this, is no goals. Okay, so when you see no goals, it means you're finished and you're very happy, you did everything right, especially if there's no red squiggle lines inside your proof. Always look for red squiggles because sometimes they get put in a different position that you would imagine, but if you just go through the proof and there's no red in it, then everything's good. With red, I mean something like this. Let's comment the last line, for example. You see red appears here on the right, and it's telling you there's some error somewhere. And here at the start of the line, there's an error that tells us we can see what the error says either by putting our mouse over it, our cursor, like this, and it says unsolved goals here at the top. Or we can look at the info view, and it also tells us unsolved goals. So it means, okay, you didn't do anything wrong, but you just didn't finish the proof yet because I commented out a line. Great, let's put the line back. Now we've seen the overview of a typical lean proof, but there's a lot going on. You will not have understood, of course, all the tactics because I didn't explain them. So now we're going to go on another file that really introduces the basic tactics one by one. To do that, let's go back to our GitHub page. So everyone managed to open the editor, online editor, and it's running. You see the info view, everything is running smoothly. Great. So back to the GitHub page. Now this tutorial actually has like two modes. There's a very fast mode, but we're going to go through the a bit more relaxed way. So we're not going to go here with the explanation and exercise files, which basically condenses everything into a single file and cuts out a few exercises. We're going to go into rewriting. So 0, 1 rewriting, which is just below. We're going to open it. And
If there's mix-up stops, can I refresh the page?
yes, it should keep everything, even your like the changes you made. If you just refresh it, you can also if the button appears here, restart file, you can restart the file. Maybe if the server completely stopped, even the button will not be here, will not be there. Now, just to make sure everything is saved, I think, okay, I have to make it smaller. Okay, maybe you want to allow this, like save my settings, but I guess that's just for settings. I think the code is actually saved automatically, just to make sure you can like copy the code before refreshing, but that shouldn't be necessary.
Is it like
Yes, I think it's saved in the cookies somewhere. Okay, so let's get into this new file. As you can see, we're importing two different files. One is like specific to this tutorial, glimpse of lean dot something something and something. The other one is from Mathlib. Now, of course, if you open your new file, you can import everything from Mathlib, not everything from the project. So you will not be able to reproduce this in a separate location. You need to have this glimpse of lean file somewhere to be imported. And here, as I explained earlier, they open real, meaning that from this point on, we can use the notation of real. We can use lemmas about real numbers without having to write real dot name of the lemma. The first thing that it prompts us to do is to use the ring tactic. So we're starting actually quite strong. We're not starting from a very simple tactic. We're starting from a powerful one. But power. Oh yes, right. Great question. So tactics are lean automations that basically allow you to do stuff with the proof. So without the tactics, you could prove something by providing the actual proof term, which is usually something not very human readable, usually very long if the proof is not completely trivial. While tactics produce some proof term under the hood without showing it to us, but Lean can see the proof term that's produced. And now, depending on the tactic, now everything we've seen before are tactics. So, for example, in the proof before, unfold is a tactic, intros is a tactic, obtain is a tactic. Some tactics let us do very simple things, like unfold does a very clear and deterministic thing. It just takes the definition you use. Now the Lean server stopped here, so let's refresh the page. If you do unfold, it's quite predictable. So there's SQL limits written there. We just substitute it with its definition. It's easy. There's no hard like search algorithm under the hood. That's the same for use. It's just a way of saying, okay, we have to prove an existential statement. I prove it by providing an example of this thing that exists. And the example in this case is that, like the concrete example is this n that I have here. And I say, okay, use n. That's also, there's no complicated automation underneath. It just avoids that you need to write some boilerplate code to introduce this n into the goal. However, there's also much more powerful tactics. Like also apply is already more powerful because it has some automation inside. We'll see that more in detail later. But ring has really a strong algorithm underneath it because it basically lets you use all the axioms of a ring. So commutativity, additivity, distributivity, and it automatically tries to use them in a smart way to close your goal. So for example, let's go here and analyze what's going on. We have 3 real numbers. And what we want to do is basically change the associativity and commute them in some way. We want to put B at the start and A in the middle and associate them like this. Oh, one thing I didn't mention is associativity. For example, for the multiplication, that's the multiplication sign, associativity works in a way that associates the things on the left first. So as you can see here, now the info view is also useful to see what is associated with what. If you go here, the things that are highlighted are this block here. And if I go here, it doesn't highlight B and C, but it highlights everything, A, B, and C. It means that A and B are associated together, and then everything is multiplied by C. So in fact, if you look at the code, this in the code, it was written explicitly. So the parentheses were put here in the code, but that's just for for the ease of the very inexperienced user, because we can just take them out and the result is exactly the same. We still have association between A and B and then C. While on the other hand, if you want to associate on the right, you have to do this manually. So you have to provide the parentheses manually. And I think that maybe we'll see in the next file is be careful because implication arrows associate in the other way. So they associate on the right. And so that can cause a bit of confusion sometimes. But let's not worry about implications for now. What we want here is to solve some very easy real number commutativity stuff. But if we have to do this by hand, let's try to do this by hand before using ring. Okay, ring. Okay, no, well, let's not, because I would have to use a tactic that's more advanced. Okay, let's just accept that ring does this automatically for us, and that it's very nice because we would have to do all the passages manually like this. Now that's an easy stuff to do, so we can just do it in probably like 4 passages or something. But ring also manages to prove much more complicated statements about much more complicated objects, because if we have something that's not a real number, but that's still an element of a ring, ring will try to apply its lemmas underneath and solve our goals for us. So let's try to write something in Lean for the first time, and the first thing we try to write is something to prove this theorem. So for now, we only know one tactic. So please, I will leave you like 1 minute, like 30 seconds to try and complete this proof for you. You can just go at the start of sorry, write enter. So you push the sorry down and write here something that you think may solve this goal.
Coming back to the start.
Sure.
How do you prove that if you want to prove associativity, it is an action?
Actually, it's it's a lemma because this is associativity of the reals. We are proving that the way we define the multiplication in the reals is actually an associative operation. Lean already knows this because it knows reals. If I remember, reals are. I think the current definition in Lean is the very classical one with Cauchy sequences. So it's all exactly like we would have done in a course. Someone was, I think there was some proposal of changing it for convenience, but basically when you use the reals, you don't care how the reals are defined, as long as there's enough lemmas about the reals to make you forget the definition. So I don't need to know that a real number is a Cauchy sequence, is like an equivalence class of Cauchy sequences. To solve this problem, I just need to know that they are associative and commutative, and like what does it mean to square something and stuff like that. And Lean already knows that all of this is true. And the ring tactic, that's why I said it's very powerful, because it doesn't just apply, like, for example, infro doesn't need any, or use doesn't need any lemma, any previous lemma. It just introduces a variable. It just needs like the logic of it. A ring needs some lemmas, and it can be made more powerful if we make the library more powerful. So if we, for example, if I have some strange constructions, and before I didn't know that it was a ring, or at least I didn't write it down Lean. Now I write the proof that it's a ring. From that point onward, ring will be more powerful. It will be able to prove stuff about this new object. So yes, it relies on pre-existing lemmas somewhere. It doesn't prove associativity by itself. It just takes stuff that's already written. Okay, so in the meantime, if you try to prove the example by yourself, very nice. Now, if you didn't, let's just see how it's done. Of course, we don't have many choices here. I mean, we just tried out one tactic and it doesn't have any variation. I mean, I cannot say anything to Ring. I can just call it. I cannot tell it, okay, use this lemma. It just already knows what to use, and we just have to write Ring, and it works. It says no goals, and this statement, which is actually a bit more complicated, I would say, than the first one because it involves squaring stuff. That's also proven in a matter of milliseconds by Ring. And now we have an error but this is not really a bad error because it just tells us, look, you're trying to do something, but you already closed the goal. It says no goals to be solved. So you don't need to write sorry. You can just delete sorry after we completed the proof. It's good to keep sorry at the end of the proof while you are writing it, so you don't get the like the error that tells you, oh, you didn't finish your proof. Maybe I take an hour to write proof. I want the error for an hour there. So I just keep sorry at the end and continue writing my passages. Okay. Now let's look instead at a lower level technique. Now Ring doesn't give us much control about things to do. It's very nice because it does stuff for us. I mean, Ring can do passages that maybe would have taken time for a mathematician to do in real life, like on paper. I would have probably done a few calculations. Instead, Ring automates it for us. But sometimes you really want to have control over what happens. And one of the tactics that we can use to have very fine-grained control is the rewrite tactic. So rewrite is written RW, and it's a tactic that lets us use hypotheses that are in the form of equalities. So let's see what this example here is about. We are introducing 5 numbers, which are real numbers, and we're introducing 2 hypotheses about them. One is called H. Okay, yes, one thing I didn't mention is when you introduce an hypothesis, you give a name to the hypothesis. And the name of the hypothesis, you see this notation, that's why it's a little useful to know like the very, very basics of type theory, because you understand that here, there's not just some random notation. We're actually saying that H is of type A equals B plus C, meaning that H is a proof that A equals B plus C. Okay, so let's just keep it in mind, like anytime you use Lean, because it's a good way of looking at the code. It lets you understand a bit better if you consider this actually a proof of this statement. The second hypothesis that, and here we can write anything that we want. Okay, H is just the name we give. We can write anything, and we just have, of course, to change when we use the hypothesis inside the code. Let's keep H for now then. So the first hypothesis is this equality. The second hypothesis is other equality here, so B equals D minus D. And the thing we want to prove is this one. We can also just tab it more to make it more evident. So this other equality between the variables. So mathematically, what would we do here? We have to prove A plus E equals B plus C, and we know how A and B are some relation between A and B and the other variables. So a very natural thing to do is to just take the goal and try to see, okay, what if I substitute A with B plus C? Since they're equal, I can do this, right? Now, how can I do this? Well, I use the rewrite tactic. And going after the rewrite, again, I suggest you go to the start of the line and you go up and down to see what changes. So first we have A plus E, and then we have B plus C plus E. So we're substituting A with B plus C. And the second thing we do is exactly the same thing, but with B and using hypothesis H prime. So we do, instead of B now, if you go under, we have D minus E. Great, now we have all the stuff that we need to conclude the proof. So here we have D minus E plus C plus E equals D plus C. So you can see very easily that the only thing you need to do is cancel out minus E and plus E. Of course, we can do it because we're in a ring, but let's not do it manually. Let's let Lean do it in a single passage. Now that's the same exactly the same example, but it's just showing us that we don't need to use one line for each hypothesis that we rewrite. We can just put them all in the same line. We write rewrite, and then with the square brackets, we write a sequence of all the hypotheses that we want to substitute with commas separating them. That's also useful to visualize how the proof is going, because you can jump into the hypothesis. So if we put your cursor after the first hypothesis but before the second one, you will see only the first hypothesis applied here. And if you go more to the right with the cursor after the second hypothesis, that also gets applied in the interview. So the same proof as before, just with a different notation with the rewrite. Okay, now let's. We can see we have 5 exercises in this file, because you see 5 yellow like dots, like yellow squares in here, and yellow means there's a warning. In this case, it's a warning that tells us, hey, there's a sorry in this theorem. Maybe be careful when you use it. I think it would be good to give you a little bit of time to solve them all together at the end. So let's just skip this for now. And let's go back to let's go back to rewrite again, but now in a slightly different fashion, because as I said, rewrite lets you substitute stuff in your goal, but you need to have the hypothesis in some way, right? Now, what if the thing I want to substitute is not one of the hypotheses of the theorem, but it's a separate theorem that I have somewhere else? That's no problem. This exact same notation can be used to rewrite that also. For example, let's see what we have here. We have some, now x is the real exponent, exponential function. So we have the exponential with a plus b plus c is equal to xa times xb times xc. That's a very easy property of the exponential. So if we know the name of the lemma that tells us, hey, the x a plus b is equal to xa times xb, we can just rewrite it inside the proof just by calling this lemma. In this case, it's called xadd. Now the names follow some conventions. They're usually the very basic names are quite easy to get used to. Maybe as the more you write Lean code, the more you get used to more like exotic notations throughout the Lean library. But for example, if I want to know what is the exponent of something plus something, I write x underscore add. Because add, that's how the plus sign is treated in MATLAB generally. And then I write, remember, this is a theorem which takes some hypothesis and gives you back some conclusions. And as I said before, an implication is just a function. So we use the exact same notation as with functions. So we give them, we give this function the arguments that we want. In this case, the argument it takes are just x and y, which are the 2 variables inside the exponent. And we have here exponential of a plus b. We see they're associated together, and then c. And so we give it a plus b as first variable and c as the second variable. So we break basically the exponent in 2 parts, but we still have a sum. So we do it again with different variables this time, because now we have a plus b. So we say add ab, and it concludes the goal. So we didn't even need to use ring this time. Again, we can do the same thing as before. We can, okay, let's first do it here. We can modify the proof and just put everything into the same rewrite line. But rewrite is a bit more powerful than that, because now we gave everything it needed. Basically, we have to give every argument to the functions. But we don't really need to do that every time. We can, for example, delete this c, and it still works. We can delete this first argument too, and it still works. We can do the same with the other arguments. And if you go to see how the proof evolves, it evolves in exactly the same way as before. So it's broken up into 2 parts, and then the first part is broken up again into 2 parts. And what happens under the hood is that write tries to take your lemma and see if it can apply it with some variables here. It doesn't know what to apply to, but it sees that in the conclusions there's x plus y. So it looks in the goal for something of the form x something plus something, and it finds it because we have x this plus this. So it automatically gives to the function the two arguments that are needed. And that's very useful because then we don't need to always give them explicitly. We sometimes need to. Maybe there's multiple occurrences of x something plus something, but I only want to break up one specific occurrence. So I may want to give the arguments to say, okay, I want to break the exponential with no 3 and 5, not the one with the 7 and 9. And in that case, we just micromanage the tactic in a more precise way. This is another example, so let's do that later. And okay, now you may have noticed we always rewritten things from left to right, meaning that if the hypothesis is A equal B plus C, it rewrites A. It doesn't try to rewrite. It doesn't try to rewrite B plus C. It tries to rewrite A. So it goes from left to right.
Yeah, I was trying to do
Oh.
x for A, rewrite x like the argument of xpad as A and B plus C was given me.
Sure, because you were trying to do something like, okay, let's say you want to put these two things together first, right? So you write exp add, and then you say, okay, I want xpad specifically with A and B. Try to do this, but it will give us an error, and let's see what the error looks like. It tells us the tactic rewrite failed. It didn't find an instance of the pattern in the target expression. Then it tells us what the pattern that it's looking for is. So the pattern that it's looking for is exponential of something plus something. This is the left-hand side of the lemma that we're using. That's the default mode. But of course, there's situations where we want to rewrite like the right-hand side with the left-hand side. And of course, that's possible, but we just have to reverse the lemma that we're using. And that's the example. We put an arrow that points left before the name of the hypothesis or the name of the theorem we're using. So, okay, no, let's try to apply to the first example. We just need to write \L and then space to insert the left arrow, and it works. So you can use, of course, lemmas in both directions. I mean, of course, lemmas which have an equality. If I have a lemma that tells me, I know the exponential function is monotone, I will not be able to use it using rewrite because the proposition is not in the form something equals something, is in the form something, like some proposition which cannot be like substituted. There's, of course, other ways to that you see shortly to use lemmas like that. So let's just skip also this example. It basically is the same thing that we just saw. It uses a lemma backwards. You see B plus C is on the right-hand side, but it still gets substituted, and then it uses another hypothesis to change, again, A plus E in D plus C, and then the proof is finished. Very, very easy. Again, I'll let you do this in a few minutes. Okay, what if, now everything we did now was to manipulate the goal, but sometimes we want to manipulate our hypothesis, right? Now, usually manipulating the goal is what's called backward reasoning. Now, to do a proof, you start from the hypothesis and you have to get the thesis. You sometimes somehow need to build a bridge of implications between the hypothesis and the thesis. And you can build the bridge either starting from the hypothesis onward, so and that's called forward reasoning, or from the goal and go backward, and that's called backward reasoning. That's usually the preferred way. That's slightly more natural to do backward reasoning in Lean, while in like everyday mathematics, maybe we have a slight tendency to do a bit more forward reasoning, but just like in usual mathematics, we also do backward reasoning. We can also do forward reasoning in Lean. One of the examples of forward reasoning we can do is to rewrite something inside a hypothesis. So we modify one hypothesis to get it closer to what we want it to be. Let's see an example here. We have this hypothesis H, where like B appears, maybe we don't want B to appear anymore because we know it's equal to D already. We just want these to appear in our context. So we do rewrite H prime, which is the name of this hypothesis, at H. And this substitutes the B with the D in the hypothesis H. Then, in this example, we introduce another tactic, which is maybe the most straightforward, basic tactic of them all. It's called exact, and it's used when you have your goal already available to you in some way. So maybe, like in this case, you have the goal exactly in the hypothesis. I mean, you have some hypothesis that has the same type as the goal. I can just tell Tulin, okay, exact H, meaning that the goal is exactly H, which I already have. And so I can close it. This works also for like more complicated situations. Maybe I don't yet have the hypothesis that which is exactly equal to the goal, but I have a lemma somewhere else whose conclusions is the goal. I can do the same thing. I can write exact here the name of my lemma, and it will work if the conclusions actually match the goal. Now, another thing that I think is the last thing that's introduced in this file is how to do calculations in Lean. So one thing we usually do in mathematics is, okay, we start with some expression, and we do a bunch of modifications to this expression. Maybe we write them like this in like one after the other, one below the other. And it's useful not only to do the proof, but also to browse the proof to see what's going on, and to have like in a single site, we can have a lot of information about the proof. And this can also be done in Lean. This is using the kite tactic. Now kite is a bit picky with its syntax. Okay, you have to indent things, right? So I cannot just write it like this. Okay, no. In this case, magically it works. For some reason, sometimes you cannot do the indentation, like a wrong indentation in kite. But it has quite a complicated backend, so apparently it works sometimes. Anyways, calc lets you explicitly give the passages that you're going to make. So you don't just give it the lemma, but you tell it, okay, now I start. Now, how's the situation here? We start from some hypothesis about real numbers and want to prove that C is equal to 0. So we start by saying chi, then we write C, so we write the left-hand side of our equation, and then we write the first passage that we want to know, that we want to prove. So we write C is equal to B times A minus D. Then we prove this equality. So we're basically doing like scaffolded proofs, like one small proof inside the big proof. So we still use the tactic mode. So we write column equal by, and we're inside a new context. So now if we go after the by, this context will be not the context of the whole proof, but the context of this specific passage of the proof, where we prove this specific equality. And in this case, we can prove it very easily by rewrite, because basically we're just using the hypothesis plainly. But the small proofs can be not so small. You can actually do meaningful mathematics inside a single calc passage. Then we do another passage here. You see, we substitute the D with A times B. And again, we do it by rewrite with the other hypothesis that we have. And then we conclude the proof. So we say equals 0. That's the conclusion that we're seeking at the start. Let's see how it is. Now the last thing we need to prove is just B times A minus A times B is equal to 0. And that can be concluded by ring automatically. Now, this is, I think it, does it tell you here? Maybe not. Okay, so let's say I'm starting to write the proof. I don't have all of this. So let's just put it below and maybe comment it. I'm starting to write the proof. Do I have to type everything and remember all this notation by heart. Well, fortunately, not completely. I can just write calc and then the question mark. So the question mark triggers an automation that suggests some code here. And we can see the code suggestion in the info view. And it's actually clickable. And we can, oops, I clicked too many times. If we click on the suggestion, it writes the correct code here. Now that's, of course, it doesn't know what are the passages that we want to do. So it just suggests us, okay, let's just conclude this in a single calc step. But we can go inside this calc step, and you see it's printed by sorry, because we don't like to have error messages flying around. So if we put if we have some code in our proof, we want to give, we want to write sorry so that it doesn't do the red squiggle thing. We can go inside here, and then we can do, actually, it tells us what to do. It says, please select subterms using shift click. So we click shift, maiuscolo in Italiano. We keep it pressed, and we click. In this case, we just have C to substitute. We say create a new step. It creates a new proof step, and now here we can write B times A minus D. Then again, we go on the sorry. We write, this time we only want to substitute this right part of the expression. So we click shift, we keep it pressed. We go on the D, which is the thing we want to substitute. We click, and we click create new step. And you see, it already writes the first thing, but it lets us substitute this. This is just a placeholder symbol with the thing we want to put here, which is A times B. So we write A times B, and then you can go inside the sorries to fill them one by one. Okay, now I think these are all just exercises to try and do, and we are over 12. So maybe we can take like another 10, 15 minutes, let's say, yes, 15 minutes. During the 15 minutes, if you want, you can just relax, or you can try to do the sorries that we've left behind. There's, you see, a few of them, like 5. Some are just a single sorry, while the last ones are multiple sorries, so one for each calc step. And of course, if there's any questions at any time, please poke me. Okay, so the first magic you basically press question mark, then you go inside the sorry, inside the small context, and if it doesn't show, try to. As I told you before, calc is quite a picky tactic. So like in this case, I'll show you this here. Now let's say I forgot to comment this out. Okay, so I decomment this, and I take this stuff out. Maybe I just left it after for my convenience. I start the calc proof. I go in here, and nothing happens. So nothing shows on the goal, no goals, and nothing prompts me to shift click and solve the problem. And maybe I get confused and I don't know what to do. It's quite confusing actually. And the problem is I forgot to comment this out, and there's an error in the proof. Now calc doesn't like it when there's errors in the proof, even if they're outside the calc tactic itself. So it will stop working basically. And what we need to do is first we fix this, we comment this, then we go inside here, and now everything works. We have our context, we can shift click. And okay, maybe you can start again. And how did you do with the exercises? Did you manage to prove some of them, all of them? Did you have any particular like struggle with some of them?
How can you create a new line in that column?
Oh, okay. You go into the last, sorry. So here I didn't write what should be here. So just try to create one line at a time. Don't leave the placeholders. It can be a bit messy. So you go into the last line. You go into the info view and you press shift. You keep shift pressed. And then while you're pressing shift, you click on the part that you want to change, basically. So for example, D, you click on create a new step. It creates a new line with a placeholder in the place of D. If you have a very complicated expression, that's very handy because you don't have to rewrite by hand all the expression. And maybe you just want to change one variable inside the very long expression in this step. So that's useful for like pacing your proof. Okay. So if anyone has had any other like problem with the proof or you didn't manage to finish it, we can look at it now. Otherwise, we can go to the next file. So I'll let you decide if someone has any preference. Okay, I guess we can go to the next file then. Now all the tactics you have used here are the ones that have been explained in this file. Now we'll introduce new tactics to do other things. And to do this, we can go back to the GitHub page. And now we go to the second file, which is 02 if and only. Okay.
Just like in this exercise, we have different way, like the calc, right? Of course, some one are faster than other. So, like, even if, as you said last time, once they have a proof, I'm okay, I'm fine because it's with type it's proven. But if you want to do it in Matlab, if you want to put your code in Matlab, you have to have an optimal.
Not necessarily optimal, but at least you have to avoid a few common pitfalls that make proofs very inefficient. Now, there's two ways that a proof can be faster. You can mean faster, like faster to implement, but of course now you're meaning faster to run, to check for the computer. And there are some advanced tactics, mainly, which can take a lot of time to compile, maybe because they do some search internally, so they have basically to explore tree, or because they have to match some expression that you give it. Maybe you leave placeholders, so you make lean try to automatically infer like the hypothesis, what the variables in a lemma should be, and in some specific cases that can take a long time. Meaning a few seconds usually. In those cases, there's some techniques to go around. Maybe you give the specific variable that's hard to find explicitly, or if the tactic produced a proof looking for a proof in a search tree, you can usually make it output the proof. So when it runs, it doesn't have to search for it again, but just like it just goes in the right branch from the start, so and it becomes much faster. So yes, there is a few techniques, but for the moment, you don't need to worry too much about them. Also, if you put some code that's inefficient into MATLAB, if it's actually inefficient, the maintainer that will check your code will tell you, look, there's this problem in here. He will also probably tell you there's this way to fix the problem, please do it. Or here you can look for ways to fix the problem, and if you don't manage it, they will help you find the most appropriate way for the situation. So now let's look at some more logic-based stuff, because we're going to do implications. Now, as I said, the implications in Lean have the same notation as functions, because they are functions that take a proof and give you back another proof. Now, here it just tells you how to write this symbol. You can do it in a lot of ways, actually. You can see what are the ways just by putting your mouse over it. Now, I usually use the /2, because it's similar to LaTeX, but you can also use /R, which is write, which is a bit faster, or if you really want to write like right arrow, you can do this. If you make a mistake and like if you press space before you completed right arrow, you just written like right A, it still understands that's right arrow, of course, unless there are two different shortcuts with the same conclusion but and the same prefix. In that case, it will just collapse to one or the other with some, they have some hierarchy. Okay, so let's go to the first example here. We're not introducing any new tactics. We're just proving this simple lemma. So we have a real number. We know that it's positive. We want to know that its square is also positive. And how do we prove this? Well, there will be somewhere in MATLAB a theorem that helps us, that tells us this, right? In this case, it's called square pos of pos. Usually, that's a notation that's a convention that's used a lot in MATLAB. When you see of, it means that the thing on the left of follows from the thing on the right of. So after of, you will have something that's related, that kind of describes some hypothesis. In this case, this pos here refers to the fact that A is positive, and SQ pos means that then the square is positive. So we have this exact lemma. We can look at the specific code of the lemma. Now, usually you will have some like complicated stuff at the start. Do not like put too much attention to this. This first thing, you don't even need to write it. This only appears here when you inspect the theorem. But if we go to the theorem, it will not be written U2. That's just the universe. But you really do not need to worry about it. Here it says that we're introducing the variable M0 as a type. It says, oh, we're putting a structure over M0 that's a monoidal structure with a zero element. We also want a partial order to be there in M0. And then we introduce a variable, which is A, which is an element of M0. We put this other structure. We don't need to know what it is. It's pos-mul strict mono. It tells us that probably you need to have a multiplication, and you probably have some monotonicity of the multiplication, probably by a positive number. But don't worry, these are super general hypotheses. You can just think of it as, okay, let us put ourselves in the real. The real numbers automatically verify all of these, and we know it because Lean doesn't complain when we use this theorem in a context where we have real numbers. Now, this is the real hypothesis of the theorem, the thing we actually care about. And you see this is between parentheses. Now, we mentioned this earlier, like in the last lecture, but there's three types of arguments in Lean. Two of them are implicit arguments, so you don't need to provide them to the function, and they are the ones between curly braces and square brackets. While the explicit arguments are the ones between parentheses, and we need to write them down when we use the theorem. In fact, here we use a theorem and we give it this proposition, which is A is bigger than 0, as an argument to the function. And it gives us back exactly what we want. Great. Now let's look at a more powerful way of using previous lemmas or hypotheses that we have, which is, okay, usually we do not complete the theorem in just one step. So we saw in the previous file that one way of reasoning is maybe you modify your hypothesis using rewrite, so you do forward reasoning in that way. Another way is rewriting stuff inside the goal, but we can only rewrite if our theorems are in the form something equals something else. But a lot of theorems are not in this form. They just tell us something. They give us, we give them some hypothesis, they give us a conclusion. And maybe we want to say, okay, the conclusion of the theorem is exactly what I need, but I still don't have the hypothesis. I don't have them ready at hand. Can I still apply the theorem and just prove the hypothesis later? And yes, we can by using the apply tactic. So here we have the same theorem as before. So A is positive, then square A is positive. And we don't have the fact, so we would like to apply it here with A being this stuff inside. So we don't have A now, we have A squared. So we need the fact that A squared is positive to apply the theorem. What we do is we use apply, and the goal becomes exactly the hypothesis that we would have needed, because we still don't have it in our hands, but we can prompt Lean to say, okay, let me prove it, but still simplify the goal using this lemma. So we apply this lemma, we apply it again because we have the same situation. We have something square is positive, just prove that the first thing is positive. And now we can conclude using exact HA, which is the hypothesis that A is positive. Okay. Now this could have been done exactly like before. So if we are in this situation here, we could have written exact, and then the name of this lemma, and then HA. But using exact, we have to do everything in one line. Exact means we are closing the goal now. This is called a finishing tactic, meaning that it can either finish the proof or fail. So if we forget to put the hypothesis, it will fail because it says, look, you don't, you're not providing me with the thing I need. This is just some random lemma. I'm trying I'm trying to look if there's an instance of this lemma in the goal, but there is not. Why? Because this is a function. Is just the lemma is the function that takes this left part into this right part. It's not the right part itself. It's a different type, so it doesn't understand. And so we use more powerful tactics. Great. Now, actually, apply can also do the stuff that exact does. So if we, instead of using exact, we write apply, this still works. So apply is strictly more powerful than exact. It tries to fill also some arguments by itself if it manages, but it can close the goal. Usually, though, if we're actually finishing, we use exact just to show, okay, we are giving the full proof of this final bit of the goal here.
What's the way to do a forward apply instead of that?
So apply can also be used forward if we do apply at. I don't know if there is an example of this in the file. Probably not. Mm-hmm. I can do apply, then the name of the theorem at HA, for example. And now this will it will not give me a new hypothesis. It will modify the old hypothesis. And basically it substitutes the premises with the conclusions of the lemma if we have the premises. And yes, that's one of the ways to do for reasoning other than, for example, that we write that we saw before. Or we will see another way of doing for reasoning. I'm not sure if it's right now or in the, oh yes, it's right now. So yeah, as before, let's skip the exercise for now. And let's look at this other way of introducing new lemma. So we saw that apply at modifies an existing lemma, but maybe I don't have the thing I want to prove in my context. Maybe I have it as a separate lemma, and I want to apply that lemma to my conclusions in some complicated way. Maybe I don't want to lose the hypothesis that I had here. Maybe I guess I will need this HA hypothesis after. And so what I do is introduce a new hypothesis using have. Now have has this notation here. I start by writing the name of the hypothesis that I want to introduce. Now let's look after have. You introduce a new hypothesis named H2. Then I do semicolon. I do colon, and then I write the type of the hypothesis that I want to introduce. So I say, okay, I want to introduce the hypothesis that A squared is greater than 0. And then what I need to do is I prove that this hypothesis that I introduced is actually true. So I, exactly like in Kite, where I have to do a new subproof for this small intermediate goal, I can do the same with have. And here I prove this exactly like we proved it before in the lemma. That's, you see, there's the same situation as before. And then after if I am outside the have, I can use this new lemma that I have, the new hypothesis, to conclude my thesis. Now, exact, I think, is even pickier with indentation. Yes, in fact, you have to indent the proof after the exact, otherwise it's going to complain. You have to go one tab after the level where you have the keyword have for the proof. Okay.
Is this the same exact thing you would do if you want to introduce a new variable, like my group is let epsilon be greater than 0?
It depends. If you actually want to introduce data, so have works well with propositions. So with things whose type is prop. If I want to introduce something that has a different type, as you said, I want to introduce an epsilon. Or maybe I want to give a name to some composition of the constants that I have here. I would use either let or set. They are basically the same thing. So let's say I want to introduce a new variable b, and I want to define it as 2 times a. I can do it with let, and now let tells me, okay, you have this new variable, which is a real number, and it's defined as 2 times a. Now, this can be a little like hard to work with at the start, usually because Lean tends to unfold the definitions you gave with let a bit too eagerly. So maybe you are doing some modifications of your goal, and Lean will, for some reason, unfold your b into 2 times a, even though you don't want it. So it takes a little bit getting used to. Now, the other possible notation is set. So instead of let, I use set. That's the same thing. It's handled internally a bit differently. So in some situations, it can behave slightly differently, but it lets you do an additional thing. Let me see what's the notation. Of course, like right now, I don't remember how to write what I want to write. So I put my cursor over set, and it will describe me what I'm looking at. So it says set the column equal t with t. So I know that what I have to write now is with, and it tells us, describes us what this tactic does. So what I can do more than let is using with HB, for example, and HB is the hypothesis that B is equal to whatever I defined it as. And so this way I can more easily handle, maybe I can write it exactly where I need it, inside the goal, or maybe inside other hypotheses. Okay, so yes, that's one way to, that's the way to introduce new stuff. Or of course, if you're developing a more like theory, maybe you want to define something like globally, and then you do a proper definition, and then you go on with the definition, or you do something that's a little bit more shallow than a definition, which is an abbrev, which is an abbreviation. Maybe I can say, I don't know, I can say twice of a real number is another real number, and it's defined as 2 times a. And I'm just abbreviating here. I can use, I don't know, have twice a, twice a is, I don't know, bigger than 0. And I can say by sorry. And Lean understands that by twice a, I mean this thing, this abbreviation that I wrote here before. That's slightly different from a definition, because a definition, like, again, it gets unfolded less eagerly. Maybe that's the main difference, at least from what I know. There's probably some more low-level differences, but both can be used quite easily. Oh, yes, sure. Yes, I didn't explain this actually. So here we gave a name to our new hypothesis. I can avoid giving a name to it, and Lean will just give it the standard name, which is this. Also, another thing that can happen is, let's say I do two new things. No, maybe A is different from 0. It will also name the last have with this, but of course the old one will have this name removed, and it's suggested to us with this cross here that this name was the old name of this hypothesis, but now it's not reachable anymore. Now the same has happened. This doesn't only happen with this, but also with any other name. For example, here we define B, and then we redefine another B. And here it tells us, look, I have this B defined, but you cannot access it anymore using the keyword B. So if you want to access something later, do not rename. I mean, do not give its name to something else because it will be hard to get to it. It's possible still to access like overwritten things, but that's a pretty low-level thing to do. You usually don't want to get into that. Okay. Okay, yes. Now we look at how to prove implications. So let's suppose we have an yes.
In like replace the goal with the premise, assuming the conclusion of implication.
With sorry, you said with by. Oh, apply. Okay, yes, sure.
So it takes an implication where the conclusion is the goal and replaces the goal.
Yes.
And what if the thing you are trying to apply has multiple branches? Does like the branch and stuff?
Yes, it will branch. Yes, this is exactly a good example of this. So let's not look at what we're proving. Let's just look at the info view at this point. We have that A is positive, B is positive. We want to prove that A plus B is positive. And there is a lemma which is called add pos that does this. Now, what if we want to apply add pos? So we have two hypotheses that are needed for the conclusions to be made. What happens is that now here we have two goals, not just one. And we could do two things. One is very not nice to read, which is just go on. Okay, we see that the first goal is the highlighted one. So now at this point, it reminds us that there is another goal, but we actually are into this one. The first one, we can just say, okay, exact HA, for example. Then we go, and this first goal is closed. You see now we have only one goal left, and we do again exact HB. Now this compile it's syntactically correct, but you see it's not very nice to read this because how can I see that I'm branching? It doesn't suggest us that I'm branching, so I have to like compile this in my head to understand that we're actually doing two separate proofs here. So what's usually done is we separate the proof with this symbol. This is just a convention. You could use just a dot, a normal dot, and it works, but usually we use \dot, which is this center dot. And it basically just divides visually the proof. And when you are inside the one of the dots, the nice thing it does, it gets rid of the secondary goal. And now you can just see the primary goal, but it doesn't really change anything in how the proof internally is handled.
I guess the syntax like I'm like sorry the first one and that.
For example, so you can add partial hypothesis. Now the easy thing is to add only the first hypothesis. So you have two hypotheses here. You know already HA. And then what happens is, oh yeah, great. We're just missing the second hypothesis. And so it prompts you to prove the second one. Now, what if instead I know the second hypothesis and not the first? I still can do it by putting a placeholder here. So I tell it, okay, try to fill this automatically. It will not manage to fill this completely automatically, but it will prompt me to prove this. It will, if it sometimes it manages to prove small stuff, but on its own applies. It tries to do a little like not only completely trivial stuff, but also some, but mainly trivial stuff. Yes, that's one way. And in general, when you put a placeholder, even in a function, for example, which is the underscore, you're telling Lean, try to fill this up automatically. I'm not giving this to you, try to infer this from the context. I can also write question mark underscore. In this case, it's exactly the same. So question mark underscore or underscore in this situation is the same. In other situation, it will not be the same. Now that's, well, let's see, it's a little bit more advanced, but let's write have. I can even avoid, okay. Oh yes, it does. Yes, you see here. What I'm trying to do is, okay, have like, let's do another hypothesis, and maybe what I want to prove is like A plus B is bigger than 0. Okay, now it compiles. And I can give it the proof. You see here, I'm in term mode. I don't need the by because I'm actually giving the full proof here. I don't need any tactic. I already have proof, but with a hole. Now I think this, yes, this doesn't work now because just the underscore, it tells Lean try to fill it up yourself, but it cannot. While the question mark underscore is don't try to fill it up, but leave it as a whole and prompt me after to fill it manually. So what this does is it adds what we need. So it adds the fact that A plus B is greater than 0, but now we have two goals. So we have to finish the goal that we had before. Now we can do it with exact H2 because we have exactly what we need now, but we still need to fill the missing detail. So the missing hypothesis, which is HA, so we can do exact HA, and this compiles. So yes, we can leave holes. But in this case, for example, another detail about have is I don't really need to give it the conclusion. If I give it a full proof, I can let Lean infer on itself by itself what the conclusion should be. But in this case, it cannot. Why can it not? Why doesn't it manage to infer the type? Because I'm saying, okay, please use this lemma, which tells us, okay, these two things imply this, and I'm giving it the second hypothesis of the lemma, so it knows that the second thing here is B. So it's exactly the B I'm giving it, but I'm not giving anything for the first hypothesis. So what can I put here as A? What is A in this context? It has no way of guessing that on its own, and so it complains. It tells me, it tells me I don't know what you want me to prove. Instead, if I explicitly tell him, he knows that A is the stuff that should be on the left of the plus sign, and so everything works smoothly with even with a hole in it. Okay. So for the last few minutes, let's just see. Yes, let's just see the implication quickly. Maybe the if and only if we manage. So I told you that an implication is a function, but right now, if I told you prove an implication, you still wouldn't know what to do. Okay, like what tactic do I use to prove the function? Now, one way is just use use a low-level proof term, but it's hard. Okay, it's possible to write a proof term for this manually, but it takes quite a few minutes to getting everything in place. So the tactic that we use to help us with that is the intro tactic. The intro tactic is used when we have a goal of the form something implies something else, and well, logically, what you do is, okay, if I want to prove that A implies B, let's just assume that A is true, and let's try to prove B. And that's what happens here. I can do intro, and let's give it a name, HPQ, for example. Now that's a complicated one. Let's try to make an easier example without all of these implications. I just want to prove that I don't know. Let's do like this. Okay, that if I have the hypothesis P implies Q, and I have P, then I have Q. As I said before, the arrows are associated in a different way than the plus or times signs. In fact, if we inspect here, you see that P implies Q is associated together, and all this other stuff is associated together. It associates to the right. So this means intro means let's try to assume that this is true. So let's assume that P implies Q as a hypothesis, and we call it HPQ. Again, we have another implication in the goal. So let's do intro. This time it's P, so maybe we can call it HP. This is a proof that P is true, remember? And now we have a proof that P is true. We want to prove that Q is true. And we're basically done. We can just do exact HPQ, HP, right? Because HPQ is a function that takes a proof of P and gives us back a proof of Q. Or more easily, we could have done apply HPQ. See, we have Q to prove, and we have an hypothesis that has as conclusions Q. So we apply that hypothesis, and now we just need to apply something to prove P, and we already have HP. So we do exact HP, and we're done. So this is how you prove implications. What about if and only if? What is, I think, yes, in 5 minutes, I think it's enough to see the if and only if, because it's essentially just a pair of implications, right? It is defined as a pair of implication, because if and only if if and only if B just means A then B and B then A. Okay, so here, actually, oh yes, now here it actually it does other things because it tries to prove it without breaking the if and only if into two parts. Let's see if there is another example of this. There is no. Okay, not a problem. Okay, yes, yeah, okay. This is an example of this. This is an only if and only if. And what do we do to break it into two implications? We can do constructor. The constructor tactic takes an if and only if and breaks it down to the two parts that make it up. So again, we have a branching. We have two goals now. So we divide the proof. Now, the thing I suggest is whenever you have a branching, you do not start proving the first thing. First, you can do the like the skeleton. You can write down the skeleton with Soris. So now I can see visually that I have two things to prove. And then I go into the first one and I prove the first one. This is, I don't know, okay, yes, that's an implication. So I can do intro H. Then I can rewrite H. And then I can do ring, for example. You see, I introduce the hypothesis of the first part of the implication as an hypothesis. I rewrite this hypothesis, and then I use ring. And here I can do basically the same. Okay, yes, a bit less than I thought. Now we don't have time to complete all this file today. Now this doesn't introduce any other tactics than the ones we've seen. So if you have a couple of minutes at home, you want to try your newly acquired lean skills to finish this file, please do so. We can discuss the exercises at the next lecture, which will be Tuesday at Tuesday morning at the same hour. So it will be, let me see the day. Tuesday. Oh yes, exactly. I was wrong. It's Tuesday afternoon at the same hour of the machine learning lectures, for anyone was at the machine learning lectures, so maybe someone that sees the recording. It will be at 2 o'clock in the evening until 5 o'clock in the evening. It will be another tutorial session. We will go on with these exercise files. We learn a few other tactics, and if we have a little bit of time, maybe we'll try some exercises that use like a bit more advanced objects like probability measures and stuff like that. So for the last few minutes, if you have any questions about either the code or Lean in general, please go on. Okay. Then I guess we can finish a minute earlier. And yes, thank you very much for being here today. And let's see, we'll see together the next lecture.